So what we just drew there was in essence the root locus. It was the locus of all the roots, or the roots of the closed loop denominator. And the way that we did it was just by brute force. Go in steps of k, calculate new pole locations, plot them, calculate a new value, find a new value of k, calculate the pole locations, plot them, and so on. And if we were to ask a computer program like MATLAB to plot the root locus for us, that's what it would do. It would just do a brute force numerical plotting of points. It turns out, however, that we don't have to do it in that brute force manner. There's actually a procedure where we can draw this root locus based on the open loop transfer function. So it's interesting that we can determine all of the closed loop pole locations based on the open loop transfer function. And we're going to learn this procedure. What we'll learn is just an approximate procedure to get a rough idea of the root locus. But if we want to get a more precise picture of the root locus, then we'll use something like MATLAB to do it for us. But it is beneficial to understand the basic idea so that we know how to modify the root locus with control. At this point, we're now going to try and explain where this drawing procedure comes from that we're going to learn. And this might be a little uncomfortable. You may not follow every piece of this explanation, and ultimately it's not necessary that you understand it completely. It's not something I'm going to ask you to do to derive the rules for drawing a root locus, but I'm just trying to, in a very hand-waving way, try to explain to you where these rules come from. And so the idea is that we can draw the location of all the possible closed loop poles for a given system, a negative feedback system, as we vary some parameter, which will normally be something like a proportional gain in our controller. And we're going to derive this procedure from the open loop transfer function. So for this system, go ahead and take a second and see if you can remember what we mean by open loop transfer function. Recall that the open loop transfer function is, in essence, the loop. It's as if we took our negative feedback system, broke the feedback signal, and straightened it all out. So in this case, we have these forward dynamics G of S, and we have these feedback dynamics H of S, and the open loop transfer function is G times H, everything that's in the loop. So again, that might be a little confusing, but try and remember when we say open loop, it's as if we mean everything in the loop. Now let's think about what the closed loop transfer function looks like for this system. It's negative feedback, so it's simply forward over 1 plus loop, where the forward path from the reference to the output has only G in it, and the loop has G and H in it. So we get forward over 1 plus loop. That's our closed loop transfer function. Now let's think about where the closed loop poles come from. Closed loop poles are values of S that make the denominator of the closed loop transfer function equal to 0. So the closed loop poles can simply be found from this equation, where this is the closed loop denominator. However, it's interesting to note that this, the G times H, is the open loop denominator. So if we know what the open loop denominator is, we in essence know what the closed loop poles are without ever actually having to find the closed loop transfer function. And so what we're going to do is we're going to assume that we have some multiplicative parameter k that we'd like to examine how the system changes with changing of that parameter. Okay, so on the previous slide we had 1 plus g of s times h of s, and so in this case this is g of s times h of s, where we factored out a k. So this is the numerator of g times h, this is the denominator of g times h with a k pulled out. And if we rearrange this, subtract the 1 to the other side, divide through by k, we get that in essence the open loop transfer function must equal minus 1 over k. This relationship is going to become the basis for the root locus procedure. Even if we had a situation where we wanted to examine how the system changes with a parameter that doesn't multiply the open loop transfer function, we could still rearrange the transfer function or this equation into this form. In that case, n and d aren't necessarily the numerator and denominator of the open loop transfer function, but we can still use this sort of procedure that we're going to generate. And so what this equation means is all of the points in the complex plane that are on our root locus must satisfy this equation for some value of k. Okay. Going back to this example of a root locus that we drew previously and recalling this relationship that we just derived, every value of s, which is a closed loop pole or a possible closed loop pole for our system, must satisfy this equation. So if we picked some value in our complex plane, some point in our complex plane, for example this point, and we plugged it in to this relationship, there would be no real valued k which would make this work. So there's no control gain k which places a closed loop pole at this location. However, if we picked any point that is on our root locus and we plugged it in for s, there would be a value of k for which these two are equal. And so that's what this says. Looking at it from another point of view, if we plotted this point minus 1 over k on the complex plane, k varies from 0 to infinity, but this in essence is a real number, so it's on the real axis, and it's negative, so it's located over here. And we can think of this in terms of its radius and its angle, or in terms of its radius and its phase. So specifically, if we thought of this sort of in polar coordinates, the angle of that complex number is equal to minus 180 degrees, where 0 degrees is in the positive x direction. And so taking this relationship here, we can split it up into two conditions. One is the angle condition. Okay. So if we picked some value of s that's in the complex plane and we wanted to test it, this is going to be some complex number, in general. If we plugged in minus 2 plus 2j into our transfer function and expanded and reduced everything, this would be some complex number that has some phase and some magnitude. So in general, if this is a complex number that we get when we plug this in, it'll have some phase and it'll have some magnitude. In order for this to be satisfied, our phase needs to be minus 180 degrees. It needs to equal the phase of minus 1 over k. This angle is also the same thing as plus 180 degrees. It's also the same as 540 degrees. So in essence, adding multiples or subtracting multiples of 360 degrees brings us back to the same angle. So the phase for a given value of s needs to equal minus 180 degrees or minus 180 degrees plus some multiple of 360 degrees. So that's the angle condition, but then we also have the magnitude, where the magnitude is simply, you can think of it as the absolute value, but it's sort of like the hypotenuse, where the legs are the real part and the imaginary part. So we need to call this the magnitude condition. Okay. Where the magnitude of the left-hand side for some value of s needs to equal the magnitude of the right-hand side, where the magnitude of the right-hand side is just 1 over k. These two conditions form the basis of all of the rules that we will develop for drawing the root locus. Okay. Before we do that, though, let's take a look at the big picture. So recalling the magnitude condition, let's think about what happens as k goes to 0. So as k goes to 0, we have a finite number divided by something that's getting very small, so this blows up. So this gets very large. In order for this to get very large, either the numerator needs to get large or the denominator needs to approach 0. And so think about what values of s will make the denominator approach 0. Values of s that make a denominator 0 are the poles. So in essence, as k gets small, this blows up. In order for this to blow up, d must get small, and that corresponds to s approaching a value of the open loop poles, because d of s is the open loop denominator. So as k approaches 0, the root locus approaches the open loop poles. And this is something we saw in our previous example. Similarly, if k gets large, if k approaches infinity, then we have a finite number divided by a very large number, and this becomes 0. In order for the left-hand side to become 0, either d needs to become large or n needs to become small. And so values of s that make the numerator approach 0 or equal 0 are what? Zeros. So as k approaches infinity, this becomes small, this becomes small, this becomes small if n approaches 0, which corresponds to values of s that are equal to the open loop zeros. This too is something that we saw. Okay? And so this gives us sort of a big picture idea of what the root locus is doing. So stated in words, branches of the root locus start at open loop poles and end at open loop zeros. Note, if we have more poles than zeros, then this includes some zeros at infinity, which are called asymptotes. And that can be thought of as, so as k goes to infinity, n goes to 0, and the locus approaches open loop zeros. It could also correspond to the denominator going to infinity, and and that corresponds to the locus approaching asymptotes. Okay? So going back to our previous example, so looking at this previous example, when k was 0, we started at open loop poles. So k equals 0, this was the location of the closed loop pole, which corresponded to the open loop pole. And as we made k approach infinity, one of our closed loop poles approached an open loop 0, and the other closed loop pole approached this asymptote.